In today's notes, we are going to look at limits and continuity. So specifically, we are going to look at limits of a multivariable function. Before we do that though, let's review what a limit looks like in two-space. So in two-space, you have your x and y axis, and you have some function of f, or some function f in terms of x. And you're looking for the limit as x approaches some value. And we have this point here then, x naught, y naught. So then as we look at our notation, what this is saying is the limit as x approaches some value from the right, and that f of x actually should not be there, of the function, needs to equal the limit as x approaches that value from the left. That's in order for the limit to exist. So the limit from the right and the limit from the left need to be the same in order for the limit at that point to exist. Now, remember though, there could be a hole here. So there could be a hole here, and the limit is still going to exist if we're approaching from the left and from the right the same value. So that is a limit in two-space. Now, if we want to look at a limit in three-space instead. So graphically, this time, we're going to have our x, y, and z axis. And we're going to have some function. So this is some function in terms of x and y. And what we're going to be looking for, as you can see in our notation, is the limit as a point approaches some value. That's actually a 0, not a 9. So our x naught, y naught, let's say this is x naught, this is y naught. So then our point ends up being here. And then what we end up doing is finding that point on our function. So our notation is saying x and y are independent variables. They're approaching some value, and we're looking at the function. Man, my notation's pretty poor here. That should be a comma. So then this value would be our limit. So when looking for limits in three-space or four-space or so on and so forth, there's two questions to consider. The first question, is there actually a point there? So is there a point at that value, or are we approaching a point? And then, how many directions or paths of approach do we have? So if we look back at this example, here's our point. We know that that's our limit. How many different ways can we approach that limit? Well, we can approach it from this way, from this way, from this way, from this way. Hopefully we see that there are infinitely many directions or paths of approach. So that's very different from what we saw in two-space. In two-space, there are only two paths. We can approach from the left, we can approach from the right. Right? And so then when we're finding our limit, if we find the limit from the right and the limit from the left, and they're the same, then we know that our limit exists, and the value of that limit is wherever that point is approaching. In three-space, that's significantly harder because there are infinitely many paths of approach. So there's no way for us to check all of them. So let's look at some examples and what this is going to tell us. So let's consider that we have some function with independent variables x and y equal to this value. We're finding the limit as xy approaches to one of that function. Okay, so in this case, first thing that we're always going to do, like when you did a limit in two-space, try to plug in. So we get -2 times 1 over 2 squared plus 1 squared, which is going to be -2/5. Okay, before we just say that that's our answer, we got to ask ourselves, is there anything funky going on around -2/5? Could there be an asymptote? Could there be any holes? Anything like that? Hopefully we know that that's not the case. That denominator is never going to be 0 unless x and y are 0. So our limit ends up being -2/5. That's the type of limit we love, the one that is easy, just plug on in. That's not always going to be the case though. So let's look at another example. So now we're looking at our same function. This time we're looking at the limit as xy approaches 0, 0. So first thing that you should do is try plugging in 0, 0. As you can see already, you're going to end up with 0 over 0. Okay, so that's a problem. That does not mean the limit does not exist. Okay? We can't just say, can't plug in 0, 0, limit doesn't exist, therefore we're done. That's not the case. If you think back to the visual we drew, there are infinitely many paths along which we can approach this point, 0, 0. And so we're going to look at a few of them. First path we are going to look for is if we approach along the x-axis. So now, remember, along the x-axis means that y is 0. So what happens then is we find the limit as xy approaches 0, 0 along the x-axis. Along the x-axis, though, we know that y is 0. So I'm going to substitute in 0. And when I do, I get 0 over x squared plus 0. So then we are looking at the limit as x approaches 0, right? Because we already know that y is 0. We already took care of that, of just 0, right? That's what happens when I simplify. So that limit is 0. What I want us to understand is this 0 is the limit from one direction. It is not our answer. So we are not allowed to just pick one path and say that that's our answer. Okay, so let's try now to look at the limit along the y-axis. So along the y-axis is when x is 0. So what this limit then is going to look like is, again, we're approaching, xy is approaching 0, 0. But now, if we're along the y-axis, where x is 0, we're substituting x equals 0 into our function. So that ends up giving us the limit as xy approaches 0, 0 of 0 over y squared. Okay, we're not evaluating the limit yet. We're just simplifying. Now, we've already handled x is equal to 0. So all that we're left with is y is approaching 0. And again, we get 0. Okay, let's try one more path. And at this point, it's not important for you to understand why I'm choosing these paths. Hopefully, you'll see why in a few minutes. We're just looking at what it means to approach along a path. So now let's look at the limit along the line y equals x. Okay, so what that means then is I'm looking at the limit as xy approaches 0, 0 of f of xy. So this is going to be the same as the limit as xy approaches 0, 0. At this point, I need to substitute in this y equals x. So what I'm going to do is I'm going to go back to my function, and everywhere that I see a y, I'm going to replace it with x. So that's going to give me negative x multiplied by x over x squared add x squared. So that is the limit as xy. Well, we've already taken care of the y, so really it's just x at this point. That is the limit as x approaches 0 of negative x squared over 2x squared. Don't substitute in yet. So this is the limit as x approaches 0 of negative 1/2, which gives me a value of negative 1/2. Okay, so we got a few different answers here. We got 0, we got 0, we got negative 1/2. So in this case, it seems that the limit does not exist. Now, from going through that example, besides understanding or seeing when it might be that the limit doesn't exist, what I want us to see is that this process was inefficient and impractical. Like we talked about at the beginning of the video, it's not going to be possible to look at every single path. Okay, so what we're going to do at this point, before we look at some more examples and talk about whether or not the limit exists, we are going to look at the formal definition of a limit, similar to probably what you did in Calc BC. Okay, so let f be a function of two variables and assume that f is defined at all points of some open disk centered at x0, y0, except maybe that point. Then the limit as xy approaches x0, y0 of f of xy is equal to some value L if, given epsilon greater than 0, we can find a delta such that the function subtract the limit is less than epsilon when the distance satisfies this. Okay, so here's our open disk, and we have some point in that disk, and we want to find the limit as xy approaches that point. So here, again, is the disk in 2 space. F needs to be defined at all values in that disk except maybe the actual point itself. And then you see if we take our limit and we add epsilon and we subtract epsilon, we get this little smaller disk that we're then going to reflect up. So I want to talk about what this looks like in 2 space, since that's what you saw in Calc BC. So in Calc BC, again, like I showed you before, we had some function in terms of x, and we were looking at some point x naught, or some value x naught, which correlated to some point x naught, y naught. And so what this looks like in 2 space is that x naught, we are going to add epsilon and subtract epsilon, and then it gives us this interval. And then on the y-axis, we have our actual limit, y naught, that's really L. And again, we have this little interval. That's y naught add delta, this is y naught subtract delta. And so it gives us an interval over which to look. It's the same idea in 3 space, except instead of an interval, we now have a surface that we're looking at. This is not something that I'm going to test you on. It's something that I wanted you to see, though. So you are not going to have to find epsilon or find delta. I just wanted you to see the definition of the derivative. So let's take this and finalize it into a theorem. So here is our important theorem. If f of xy approaches L as f of xy approaches x naught, y naught, then f of xy approaches L as xy approaches that point along any smooth curve. So what that's saying is if f of xy approaches some value, then it's going to approach that value along any curve, along any smooth curve at that point. On the other hand, B, if the limit does not exist along some smooth curve, or it has different values along different curves, then the limit does not exist. That's what we saw in example 2. We looked at 3 different curves and got 2 different values, hence limit doesn't exist. So here's what I would suggest when you're approaching a limit. Plug in the values, so plug in the x and y, and if you get a value, great. If you don't, then in all likelihood, the limit does not exist. If that's the case, you need to show that there's a path where the limit doesn't exist, or you need to show that you have 2 different paths with different values. So let's take a look at some examples here. If we look at example 3, first thing that I would do is plug in 1, 2. So we would get 5 times 1 squared multiplied by 2 over 1 squared at 2 squared. So we get 10 over 5, which equals 2. And again, before you make sure that that's the case, is anything funky happening around 1, 2? Are there asymptotes, holes? No. So our limit there is just 2. Now, the second example, if we plug in 0, we're going to get 0 over 0 squared, which is not helpful. So then you might ask yourself, well, can I simplify this? The numerator factors, the denominator doesn't, so I can't simplify it. This would suggest to us that maybe the limit does not exist. So then what we're going to have to do is we're either going to have to show a path where the limit doesn't exist, or we're going to have to find 2 paths where the limit is different. So that's what I'm going to do. I'm going to start with the path x equals 0. So if x equals 0, what I'm going to do is I'm going to go above and I'm going to plug in a 0 for x. So when I do that, I'm now just looking for the limit where y approaches 0. So I get negative y squared over y squared squared. So this becomes the limit as y approaches 0 of negative 1 squared, which just gives us positive 1. Okay, at this point you might be tempted to do y equals 0. It's going to give us a similar value. If I try instead along y equals x, if I get rid of that y and I now just have x equals 0, so this will give me x squared subtract x squared over x squared add x squared quantity squared. So this then becomes the limit as x approaches 0 of 0 over 2x squared quantity squared, which is 0. Okay, so because these two values are different, what that tells us is that the limit does not exist. Now, I was able to get it in 2 paths. It might take you a few more. You're going to have to do a few of these to get some intuition of the paths that you're going to want to try. It's not just x equals 0, y equals 0, and y equals x. Sometimes you're going to have to choose some different ones. So at the bottom, to prove that the limit does exist, you basically have to be able to calculate it. So if you can plug in the numbers and you get a value for the limit, great, the limit exists. If you don't, the limit probably doesn't exist and you have to show why. Okay, so last thing that I want to talk about is continuity. Okay, continuity in 3 space is going to be very similar to continuity in 2 space. A function f of xy is said to be continuous at some point if the function is defined at that point and the limit as we're approaching that point is equal to the function value. 2 quick comments. If f is continuous on some disk, then f is continuous at every point in that disk. If f is continuous everywhere, that means that f is continuous at every point in the xy plane. And then we have a theorem, and we'll look at our last example. Consider some function that is the product of a function of x and a function of y. That is continuous at some point if g is continuous at x naught and h is continuous at y naught. And then compositions. Compositions are continuous. For example, if we have g is a function of h, if that inner function is continuous at x naught, y naught, and the outer function is continuous at the inner value. Okay, so we've got 2 last examples, and that'll be it. So this first example, we can write this as a function of x multiplied by a function of y. Our function of x is 3x squared. Our function of y is going to be y to the 5th. And so what we notice is that g of x and h of y are continuous everywhere. Because those are continuous everywhere, that tells us that f of xy is continuous everywhere. And again, you're looking at continuity the same way you did in Calc BC or Calc 2. Is there ever a place where the function is not equal to the value or the point? Okay, and then if we look at B, we have a continuous or a composition. So we already know that 3x squared y to the 5th is continuous everywhere. And that's from above. Then sine of some value, we'll call it u. So sine of something we know is continuous everywhere. Therefore, f of xy is continuous everywhere. Okay, and that is our notes for today. If you have any questions, please make sure you write it down and bring it to class. See you soon.